are showing up eventually. Okay, so now that you've got some idea of the aromatic reactions from video sources, how do we use them? If we have to put together something complicated, how do we do it? Aha. So, let's take an example. Okay. Let's take this one, which you should have no idea how to do, because we haven't talked about carboxylic acid chemistry, so making amides is not something you should know how to do yet. You'll get there. Not yet. This is a precursor to the antipsychotic drug Abilify. It has something hanging off this side eventually, but this is the main aromatic piece that has to be made. For our purposes, that's going to come back to this. Which is what I would actually need to be able to make the carbonyl group that I can then wrap around onto the nitrogen to make the amide and be done with it. You can't make the left one yet. You should be able to make the right one. And what are we going to start with? That's a good question. Since methylation is actually pretty hard to do, let's say that we will start with toluene instead of benzene. You can make methylbenzene, it's just not as direct as putting other alkyl groups in place. So we could start with that. Reality is you'd probably start with that and the alcohol in place, but I'm not making this too easy. You can buy the alcohol with the methyl group para to it pretty cheaply, but this isn't about cheap, this is about thinking. So, where do I start? And what do I have to do? What are the big questions?
Whether the substituents are ortho or para or methyl directly.
Okay. That's one thing I have to think about is, for the most part, the only reactions that are really useful ones involve putting things in as electrophiles on aromatic rings. There are very rare other reactions, but for the most part, we're having to do it as electrophilic aromatic substitution. Which means I have to consider the idea that directing groups are going to put things in a certain place relative to other substituents, and I have to consider that in terms of the order that I'm going to do things in. Because it may not give me what I want if I don't do this in the right order. Now, if I really wanted to be mean, I would say do this without making any other isomers. Which actually might not be possible. Ooh, yeah, it is. Yeah. I've been looking for a use for this reaction for years, because it's in the book, but I never talk about it because I couldn't figure out how to use it. I just came up with one. Good. All right, make this with no other isomers. Now, the only obvious thing here, and it's also one which you know is a liability, is that halide. Because It's on a benzylic carbon, so it's going to be very stable as a cation if it gets knocked off. It's also primary, so that's going to be subject to SN1 and SN2. So I'm not going to have that around for long. That's going to probably be the last thing I do, because it's going to get a mess. It's going to make a mess. If I leave it around too long, especially under the type of brutal conditions that I'm using to do other things with that aromatic ring, I could have a problem. Well, we know how to do benzylic brominations, right? How do we do it?
With an iron.
Huh? That's aromatic. How do I brominate next to the ring? Yes. So, conditions? But you know at least how to do it. You're probably talking at BR2 and ultraviolet light, so that you'll end up with bromotoluene and HBr, which you then remove by extraction. Regardless, if we have a benzylic carbon, we can do the bromination without really affecting the ring at all. So, because that's a very easy substituent group to knock back off, we're probably going to put that in late. Okay. So if we're going to think backwards a little bit, we're probably thinking backwards from breaking that to this. Which coincidentally was already present in my given starting material, so I don't have to worry about that group. I just have to not do anything else to it until I need it. All right, now what? On this ring, I have two substituents that are now meta to each other that are both ortho and para directors. Problem. And no mixtures allowed. Thou shalt not bring the evil M into my chemistry. No mixtures. So how do I do it? And I'll admit this is not a nice question.
PHP is a meta director.
No.
No.
Ortho and para.
Oh, okay. So from CHP.
Hyperconjugation.
Yeah.
It's the only one that's not a resonance. It's the alkyl group is a hyperconjugation, but it does the same direction for the same reason. It can help stabilize a cation, but not by resonance. Okay. How do I manage to do this? Forget about the no mixtures bit. That is a little tricky. It's possible, but it's tricky. Let's talk about how I'm going to do it at all.
First you.
There are actually two ways that you can probably do it without worrying about mixtures.
You can use sulfonation if you want to get rid of the mixture. So you put the sulfur at the para since it's 99 to 1. And then you attack with the nitration. Since
Hold it. Hold it. You're close. You're close to the no mixtures method. Very close. Sulfonation gives you 99 to 1 para to ortho because it's just a huge group. It's a meta director. This is an ortho director. They're both sending me here. So the next reaction, the nitration to put the nitrogen in place, puts me here with a nitro, a methyl, and a sulfonate.
then you remove the. Do we convert the nitrate? Do we release the nitrate amide group prior, or we connect the?
Probably not yet. I probably wouldn't take the nitro down to the amino yet.
So we'll just.
It really shouldn't matter, but let's just save that for a moment. Okay, now what?
Then we remove the sulfate with an acid.
And what was there then? So it just ends up as an H.
As an
Okay. That's one way. Dilute acid and heat, and we'll take the sulfonate back off. It was a temporary blocking / directing group that we didn't need. Okay. Now what? We only have two methods really to put in that oxygen. One, a Friedel-Crafts acylation followed by a Baeyer-Villiger oxidation. Two, a nitration followed by a reduction and then a diazotization. Okay, both have some issues. What do we do now? Right now, the ring is set up to direct where I want to go, which is para to the methyl group, meta to the nitro group. They are, respectively, an ortho and para director and a meta director. So they're directing to the right place. But you knew it was coming. That's why I backed off the no isomers problem, because this is tough. It's not an easy question. And I'll tell you, I've got this on my brain because I was looking up the synthesis for Abilify. I just look at random drug synthesis to keep myself sharp. And they don't actually say how they make that thing on the far left. It's not that bad, but the point is, they don't tell you where they're getting it or how they made it. So I started putting ways together to make it, just to see what would come out and be cost effective. And still not great. No matter what I do, it's not a great synthesis. So I don't think it's a coincidence they're not saying how they got it, because they'd have to admit that it's not really a nice looking synthesis to make it, and probably not cheap. But they've been at it for 20 years now, so they probably have some tricks they're not talking about under, under the manufacturing tarp somewhere. Or maybe it's natural, I don't know. It doesn't look like anything that I've seen before, but that doesn't mean it doesn't exist somewhere. Okay.
You don't really, is it a bad thing to start with a phenol?
You mean start with hydroxybenzene instead of toluene?
Yeah.
Generally, this type of question specifies a starting material. Reality, all right. As I said, this is more of a thought question. This is very cheap. We could buy that and have 2 out of 3 in place. But it doesn't answer the problem that we're still facing, that hydroxides are much stronger activators than methyl groups, which means your next group going in there is going ortho to the oxygen. Wrong answer. So now what? We're still going to have a challenge. It's just a slightly different challenge than this one. Okay, for this one, my 2 methods for putting the oxygen in place. Friedel-Crafts followed by Baeyer-Villiger. Is it going to work? And the answer is... Come on, you guys know my default answers. Electronegativity, resonance, cation stability, and no. I just ask you a yes/no question. What's the answer? No, it's not going to work. Why not? Friedel-Crafts reactions do not work if you have a strong deactivator on the ring. The nitro is about as nasty as it gets in that category. You ain't doing a Friedel-Crafts on that ring for any reason. It will not work. If I take it down to the amino, then it's no longer a meta-director. So I screw up and I end up in mixture land probably. Possibly. I might, well, I can definitely do a nitration. I could put another nitro in, but then I have to try and get one nitro to do one thing and do something else with the other one. Possible, but again, not likely to be fun. Likely to be very problematic. So now what? Ew, this is not pretty. There is one, which as I said is very obscure. Your book has it in it. I've never really found a good use for it until I started writing this out, and I realized, wow, that's where I could use it. It's weird, but it works. You can do an alkali fusion on this, which basically involves heating it up with like solid sodium hydroxide. Not exactly kind conditions. But since we have nothing that's going anywhere, we get away with it. If I do that, what I replace the sulfonate group with instead of an H is an OH. No. That is a weird case. And it's one that probably is not widely acceptable to doing a lot of things because it's extremely harsh conditions. It's not even got a solvent in it. If you had anything that could eliminate or substitute, that will chew it to pieces. So that is a very limited case example. But it just so happens this is a case where it would work just fine. There's nothing for the hydroxide to do otherwise. It's not going to go after the nitro group. It has nothing to do with the methyl group. It's not a strong enough base. So all it can do is that. That case gets me the no isomer version, but it's not pretty. Because it's not a normal reaction. It's one I didn't talk about in the videos. Your book has it in it. It's kind of like a footnote. Yeah, this will work, but most of the time, it's a really bad idea. Because if you have anything complicated around, neat solid sodium hydroxide at 100 degrees plus is going to do really bad things to most functional groups. Not these. So then all I got to do is reduce it and I'm done. So I take it with iron hydrochloric acid and I'm done. Well, I have to do the bromination, but that we're not worried about because that's a clean reaction. Again, it's a reaction that could cause problems, but doesn't have anything to cause problems with in this case. There may be other pieces to this puzzle. This may be how they do it. It certainly would be cheap. Nitration is not fun on a big scale, but as long as you don't let it heat up, it's safe enough. It's kind of nasty to dispose of this stuff, which we'll do, but it's doable anyway. All right. So then what? Let's say that that little Trivial Pursuit thing wasn't in your brain. It wasn't. So now how are you going to do it? We can play a little game here. And it might work. It's probably not the best of ideas, but it is an idea. Would not be something I would be overly proud of coming up with, but let's say that we're here. We've taken what John had said and we're here. We've got one group in with no mixtures. Now we just need to get the other one in without a mixture in a way that gives me an alcohol. I can't do the Friedel-Crafts. I can do a nitration, but if I do that now, I have two equal nitro groups. One of them's a little more sterically hindered, but generally things like iron HCl to take it to the amino is not going to care. So that's not really going to help me. But there is an option. This. Take it down first. Right now, that amino is an ortho and para-directing group. But what happens if I protonate it? Because if I put it in nitric acid, that's a base. It's going to get protonated really fast. Then what? Why?
Because it will decrease its electron density, therefore it will draw more electrons from the ring, making it.
How does it decrease its electron density if it's protonated? What does that mean? You're right, but I'm playing devil's advocate. I want you to say the magic word. One of my 4 favorites, and it's not no. It's neutral right now. What is it when I protonate it? It's a cation. If it gets protonated, which it will, under nitration conditions, very fast, it's a formal cation. Now, it's a meta-director, but it may be strong enough to shut off the Friedel-Crafts reaction. I don't know. Probably it is. As far as I know, the Friedel-Crafts reaction doesn't work with any meta-directors in place. But it doesn't mean the nitration doesn't. The nitration doesn't care. The nitration is one of the most brutal reaction conditions that we'll ever see. It will work on anything aromatic. It's brutal. If I do that, I end up here. After I neutralize it, now I still have 2 nitrogens, but they're in different states. And that I can work with. Because I can protect the amino nitrogen and then work with the other one. So nothing will happen to the upper nitrogen, and I can convert the bottom one into an OH. I'm not sure what you would use. The common one you use is there's an amide, because they tend to be very stable, so you would make it into something like this. I'm not sure that would survive what we're going to have to do to the nitro, because that's a pretty harsh conditions. But you could probably use some different amide group here, some different protecting group here, and you'll find something that will survive. All that's doing is just keeping the lone pair of the nitrogen from getting in our way when we try to do something else. That's all it is. So then I can take the other one out to the amino. And then to the OH by diazotization. So those are ways that basically will still avoid mixtures. Because getting something to go into an ortho position when there's one that's not ortho is difficult. So what I mean by that is technically the nitro in this step could have ended up next to the methyl group. But this is harder to get at than this. If you get a mixture at all, it's going to be dominated by going to the easier spot. This is harder to get to. The methyl group does have a presence size-wise. It's not that big, but it's still there. Do you want to go over a small obstacle or no obstacles? Chemicals look at it the same way. They're going to avoid stress. If they don't have to get into a sterically busy place, they're not going to do it. Okay. Are there other ways to do this? We basically took John's lead and just went off in a couple of directions from it. Could we do it putting the nitrogen in place after the oxygen? And that's an important question because I will bet you that's their real starting material. So we could either go Friedel-Crafts or nitro, doesn't matter which, to make this, the alcohol. I will bet that's the real starting material. I might be wrong, but it would be where I would start. But now I have a problem, because I need to put an electrophile next to the weaker director. By that I mean electronically, if I nitrate this as is, I'm going to get more than 90% of it next to the oxygen. Very little of it's going to go next to the methyl. Electronically, it's better off next to the oxygen, and sterically, the OH group is smaller than the methyl group. So it's going to win in both cases. So I have to go against that somehow. I can't go against it electronically very easily. Not really. Or can I?
Can you make it a cation?
Huh?
The hydroxide. Can you make it a cation, just like what you did with the ammonia?
It will get protonated, but it's not this. It's too exchangeable. It's not basic enough for that to hold the proton in essentially water. It'll exchange relatively fast. The nitrogen won't. The nitrogen will hold on to it, and therefore it really has an effect. The oxygen will not. Exchange, that is. Well, let's back up a step. What if I start from that? That will eventually let me get the oxygen. Can I control the nitro now? And the answer is yeah, this one's easy. The acetyl group is a meta-director. So this is the only place it's going to nitrate. So that's going to get me here. So then I have to oxidize this and reduce that to get what I want, but I can get there that way. But like I said, that's not so simple. This is cheap. I can probably go in our stockroom and find a gallon of that stuff, paratoluol alcohol. So, is there a way I can do it from there? I can't really modify the electronics of that O once it's already attached to the ring. You can sort of control the nitrogen once it's attached, but that doesn't really work for the oxygen. So, if I want to start from that, I'm not using electronic tricks to win it, because I don't have any. What can I use? How?
Make it bigger so that it first you decide to make the attachment bigger.
Okay. See what I've done? I've created someone who knows what he's talking about who's afraid to say it. You're right. You're right all along. Yes, I can put a very large protecting group in place, so that's going to take this tiny OH group. If I put something big there, it doesn't change the electronics by much, but if I put something, like this size off the side of it, then getting to those ortho spots is really tough. So then the only place to go is meta, or ortho to the methyl group. When you can't win something based on electronics, the only thing you have left is size, bulk. All right? If that doesn't work, and the electronics are against you, find another way. Because tinkering this way ain't going to work. In this case, I still have a ring that's activated enough to do the reaction with, but I just want to keep it from going here. So I make that site hard to get to. And then the only place to go is the other ortho, which is still activated because it's next to the ortho-directing methyl group. Not as activated, but it's accessible. You can get to it. Okay. Make sense? Now, I said this before, but I'll reiterate it now because I think for the first time you can really see it. One of the reasons I think that the medical tracks require this course is that it's one of the only courses in all of the sciences that requires you to learn nonlinear thinking, that there may be more than one way to get to the same spot, that you have to think based on the problem instead of based on a single canned, physics equation answer for a ball dropping off a building. There's one answer and only one answer. There's no other way to go about it. There's no other way to get to the answer. There's only one linear track to answer that type of question. When it comes to this, I think they put you into this kind of thing because you will face problems in the medical sciences and even in the chemical sciences, as obvious as here, that are not so simple, that there may be different answers to for different reasons. Sometimes